In this problem, we're going to not repeat repeated work by implementing a relatively simple optimization technique. In this optimization, more commonly known as common expression elimination, let's say we're given this snippet of code. If we look closely, we can see that the values of A, B, and C don't change, yet we recompute it when we calculate Z. So we're doing two additional addition operations than we need to. It's perfectly possible to replace that sub-expression with the variable x. That way, we can take advantage of the fact that we calculated x and avoid the additional work. Keep in mind that optimization was only possible because the values of A, B, and C haven't changed since the last time we used it. Here I've changed the middle statement to be B equals 2. That means if I did the same optimization, where I replaced this with x, it's very much possible that x doesn't actually equal A, B, and C added together. So our strategy for solving this is going to be very similar to what you would do by hand. We're going to go through each statement one by one. And in this scenario, let's say we're going to remember that we've already calculated the values of A plus B plus C, and that happens to be stored in X. That way, if we see a request for A plus B plus C, we can simply replace it with X. However, at each step, we also need to keep track of what values have changed. Here we can see that B equals 2 now invalidates A plus B plus C because we use the value of B there. Let's get started. Code time. So here I have the code for a solution. The first thing we have here is a helper function that returns a list of all of the variables used in an expression. That way we can feed it A plus B plus C. It'll return A, B, and C in a list. That way it makes it much easier to check if new statements invalidate a cached response. So here we have our optimize function that takes in the abstract syntax tree. First thing we do is declare our empty data structures. First thing is the dictionary that has the saved calculations. And then we have the resulting optimized abstract syntax tree that starts out empty. So we're going to go through each statement in our abstract syntax tree and extract a little bit of info from that statement to make it easier to reason about and write the code. The first thing we do in this loop is to check if the right-hand side of this statement has already been computed, and we have a version of that right-hand side that doesn't have any values that have been changed. That means that we can use it. If that's the case, we are going to create our new statement with the simplified right-hand side. Otherwise, we're going to remove the saved expression calculations that use variables that we modify in this statement, and then we're going to update our available dictionary of saved calculations. And before we're done with the loop, we're going to add this new statement onto our abstract syntax tree, and once we're done with everything, we're going to return the result.